Hello, am I audible?
Yeah, hi.
Okay, so let me just share my screen. So, hello everyone, my name is Hiram Chandelier, and currently I'm a data science intern at Crowd Analytics and also a NLP research intern at DRDO. And I recently started exploring this field of NLP about 6 months ago, and today I'm going to share whatever I've learned and whatever you can learn from it. So today's topic is about text analysis. We'll be learning about what is text analysis, how ML fit into it, and how you can handle various other things. So, yeah. So in this session, we'll be basically learning about text cleaning, how you can prepare your data set, clean your text in order to extract remove all the noise or unnecessary information from it to just create a quality data set from it. Second, we'll be learning about feature extraction. You can't just feed a raw text to the ML model, right? So we'll be learning about how we can create vectors of those sentences and create it into a form that is more suitable for the model to use. Third, we'll be understanding about how text classification works, and we'll actually be seeing a code demo for this, and we'll be seeing how you can use multinomial libraries for classification of tweets, whether they are positive or whether they are negative, right? So next thing, in the end, we'll be having a basic introduction about how word-to-vec works and a bit about RN using RNNs for text classification. So these are the agendas. First, we'll learn about text analysis, removing noise, each and every pre-processing step that is required, then training the model word to vec, and then if you have any questions regarding anything, we'll be learning about that. We'll be talking about how you can move forward after this. So that's also. So what exactly is text analysis? So text analysis is extracting any sort of information or insight from the text that you're given. So it could be anything, like you can maybe classify it into some data set, rate tagging, the review tagging, right? You can say, what is the rating of the a review that I'm provided. So let's say you have Amazon product, you have certain reviews associated with it. You can find out what sort of text is related to which sort of rating. So one thing is that one very popular application is sentiment analysis, where you classify your text into positive or negative sentiment, sometimes even neutral sentiment. So that's something. And text classification divided into various categories. It's basically any sort of categories, maybe news categories or any other sort of categories that you may find. But one question is how ML fits into this, right? So we all know like ML can capture patterns and trends in the data set with respect to columns, right? So if we are able to provide just provide a text to the ML model, maybe it can relate to, yeah, so this is the sentence structure, and if this word is somehow in this form, or maybe in this much frequency, this must be a positive sentiment or this must be a negative sentiment, depending on that. But there are a few challenges that we have with this. We can't just give raw data to raw text to our ML model. It can't process strings. Most ML models can't process string as it is, right? So we need to convert these texts into some numeric form so that our model is able to understand it, right? But and in order to do this, we have a solution. We do text reprocessing, and in text reprocessing, we have certain steps. Now, the steps that I'm going to provide to you are not in not a particular order. Like you have to do this first, do this first. You can feel free to do any step first and then move on depending on that. And that's what we'll be seeing in the code too. So why do we need to pre-process data? First, I have already told, like you can't just feed a raw text to the to the data set itself. So that's the first point. You can't you pass the string to the model as it is. So you need to first convert it into a form that is recognizable by the model, right? And second is removing unnecessary details, right? So let's say you have comma in the data set. Existence of that comma may be important in understanding the structure of the sentence, but it's not providing any meaningful insight regarding the sentiment or whatever you want to classify it. So you can just remove it, right? And in the same way, you can also remove other details like hyperlinks, URL per se. Maybe the content of URL may be important in understanding the sentiment, but the URL itself is not useful in understanding that. So you can remove that too. And these are the few steps that we'll be trying to understand how we can do this, and what are the steps to proceed with this. So first, not the first, like one of the things that you do is remove noise from the text, and removing noise includes removing punctuations from it. So like comma, some sort of symbols that you may have, you can remove those. And in order to remove those, you can use regex, simple regex, right? So if you are working with NLP or you plan to work with NLP, you should be at least familiar, vaguely, not vaguely, briefly familiar with regex, at least basic regex. Second is removing numbers. So numbers may, in order-wise per se, they can provide some insight. But when you're talking about ML models, most take treat the data sets, the columns independently. So existence of 20, 10, or any sort of number may not be very helpful in providing a very meaningful insight regarding the text sentiment. So you can remove numbers too. And third is removing hyperlinks. So hyperlink, let's say you have a URL to, you have a tweet and you are suppose uh, link to a GIF or something. Maybe that GIF per se may have a positive or negative sentiment, but that URL itself doesn't contain that. So you can remove those hyperlinks, and in order to remove those, you can use the library called LXML. We'll be seeing how you can use this. And you can do that with regex, but with regex there may be some let's say there might be some tag that's unopened, unclosed or something, so that regex can't deal with unless you specify it. So it's usually better that you use xml or beautiful soup somehow to remove those. Next thing is domain specific preprocessing. Now, the word might be scary, but it basically means that different scenarios require different sort of preprocessing. So if you're using Wikipedia, like Wikipedia might be fairly, organized. You have a very organized text with you. So you might not need to do all of these. You just need to convert those features itself. Basic lowercasing and simple steps like that you can do. But there might be different scenarios require different sort of preprocessing. So, your text data usually comes from internet, which is the biggest source of text that you have right now to extract from. And not every time you are going to get it in the format that you require it. So if let's say you have a tweet dataset or Reddit dataset, which usually contains emojis, right? So emojis convey a meaning, right? So let's say you have, I love this product, right? And you have a smiley emoji to it. So that emoji might be able to convey some sort of meaning. So usually you don't remove emojis. Instead, you convert them to a text. And in order to do that, you can use a library called emoji, the same name, emoji library, to demojize the emoji to the text form. Second is spell correction. So many times, especially when you extract data sets from social media, they might not be very grammar friendly, right? The spellings might not be correct. So you can correct the spellings too. So you can use PyEnchant library to correct the spellings, right? And third is hashtags. Now this is very uh, different. You have to experiment with this. Hashtags may or may not convey some sort of meaning to the data, your sentiment. So you can try with both by removing hashtags or keeping the text part of hashtag and then testing out your model. So you can use regex to remove hashtags from it. So that's it. And lastly, many times what happens is you might end up with some sort of HTML tags from it, right? So you usually have, let's say that you have a text form and you have a VR tag in it, right? So you can remove those tags, and to that you can use LXML to do so, right? And stop words. Now, what are stop words? Stop words are basically words that provide a structure to a sentence. So let's say is, the, my, and. So these may add a structure to your sentence, maybe make it more meaningful to the human, but they are not exactly very, insightful in providing information, because they're very frequently used in every sort of text. So let's say if I have five sentences and all of the five sentences have the word the, then I can't really tell that, yeah, this is the distinctive feature that is going to be able to classify my positive sentiment or negative sentiment. They might form a structure to the sentence, yeah, make it more meaningful for us, but yeah, it's not going to be very helpful to the model itself. Now NLTK has a list of stop words associated with it, and you can use NLTK to get the list and use that list to remove the stop words from your data set. Now, stemming versus lemmatization. What is stemming? So let's say you have three words. First word is go, second is going, and third is gone. Essentially, all the three convey the same meaning, that someone is going somewhere or something is going somewhere, right? So when you have all the three, and let's say you don't, you can convert it to a single root word. All of three basically can be converted to go, right? All of three basically are saying that person is going somewhere, so you can reduce all of them to go. And why do we need to do, and this is basically stemming, but when you do stemming, usually many times it happens that the word that you get is not going to be of in English vocabulary. So let's say you use photo stemmer, which is a very popular stemmer in NLTK. You use it over a word called amazing. So that word amazing is going to be converted to amaze, AMAZ, not ZE. So AMAZ is not a part of English vocabulary. So that's basically stemming, converting the word to its root form, but that word may or may not be a part of English vocabulary. Second is lemmatization. Now, lemmatization is same as stemming, right? It also converts the word to its root form, but in here, the word is a part of English vocabulary. And to lemmatize, you can use lemmatizer that's also available in NLTK. But this is computationally more expensive. So depending on the task you have, or make some experimentation, you can try whatever suits the best, stemming or lemmatization according to your task, right? So why STEM anyways, right? So we know that machine learning models are, able to, the amount of feature increases, the ML model tends to perform, sometimes better. But if there are too much features, the ML model may be, able to not perform very well on it. So first thing is to make the data set more dense. Like if you use stemming, your features are going to be reduced by by two to three times, right? So that's something to reduce the number of features in it. And yeah, there might be some downsides to it, like when you stem, you may be removing some information from a word that may provide to be helpful, may or may not be provide to be helpful. So this is one thing, but usually stemming performs really well, especially when it comes to ML, right? Yeah. So contractions. Now, what exactly are contractions? Contractions are basically abbreviations of one to two words, right? So let's say there is a word called I am. So you can write I am as I am, and he's as this, and she will as she will. So these are basically contractions, and these contractions you can expand them to this form: I am, he is, she will, and then you can do whatever you want. But usually, should you be removing contractions? I'll say if you're using you are doing a classification task, so you'll be essentially ending especially in ML with ML models, you'll be ending up removing the stop words. So if you break them, they are going to be removed eventually, like I, he, she, will, is, am. These all are stop words. So it may or may not matter that much. But yeah, contraction, expansion sometimes are helpful in other sort of tasks, right? So that is that. And let's go over what a text preprocessing pipeline looks like. So these are just steps that I'm talking about. There is no hard and fast rule that you have to follow this order only. You can try and experiment with doing this first and that first, and whatever you like, and whatever suits your data set the best. So yeah, first is removing noise, as we talked about, removing number, punctuations, URLs. And URLs you can remove with all of these can be removed with simple regex. And transform any abnormality. This is basically spell correction, demojizing, removing HTML tags, process any hashtags if there are, remove or keep it, whatever you want to do with it, depending on the task that you have. And lowercase and splitter. So if you have two words, capital T O and small t o, they both are basically conveying the same meaning. So you can convert all of them to lowercase. So there is any capital, dependency over capitalization of a word or a particular character, that can be removed. And next is converting them to list. Now, in order to remove stop words, you have to basically go over each word and tell if this is a stop word. If it's a stop word, remove it, else keep it. So for that, you need to convert the text into a list of words, and this process is sometimes referred to as tokenization, right? Next is removing stop words from the list. and third is stemming limitizing the data set that you have. And last, we have join the data set and return it. So if you have the list, combine it to a string again and then return it in a function you have, right? Next, we are talking about frequency-based embeddings. Now, frequency-based embeddings, basically you have two types. First is count vectorizer. So count vectorizer is a utility in sklearn that you have, which is going to convert a text into a bag of word representation. And bag of word representation is nothing but a collection of vector numbers that is going to define how much is the frequency of a particular word of that index. So let's say at index we have the word apple, and the entry there is 3. So it's going to say apple occurs 3 times in this text. So we'll be taking a look at this in depth, right? So it converts each entry in the text that you have to the corresponding frequency that it has, right? Next is TF-IDF vectorizer. So TF-IDF vectorizer basically converts. It basically does the same thing. It also converts a text, a sentence to a vector form. But this time, at each index of that word is going to be the TF-IDF value of that particular text. In order to calculate that, you first calculate the term frequency, which is basically the number of times that word occurs in that text. So let's say apple occurs 3 times in the text, right? And the length of that text is 8. So term frequency will be 3 by 8, and into log of n divided by dfi. N is the number of text you have. So let's say you have 3 texts, so n will be 3, and dfi is the document frequency, which is basically saying that in how many documents does this word occur. So let's say apple occurs in 2 texts, and in word text it does not occur. So df for apple will be 2, and since there are n we have 3 texts there, so this idf will this is the formula for idf, which will eventually become to log 3 by 2. So why is this different from what other information does this provide to us? So in count vectorizer, we only focus on the text itself, but in TF-IDF, we are going to look at the whole corpus itself. We are going to find how much calculation. So if a word, let's say apple, occurs in most of the sentences, it's not going to be conveying a particular meaning to the model itself. And sometimes if there are any rare words, it's going to provide more weightage to it. So that's one of the advantages of TF-IDF vectorizer. So
Hi
let's
Hiram, sorry to
yeah.
interrupt. Can you please explain the form? I mean, the DF word was not very clear to
Okay.
me.
So we'll be taking a look at the formula in depth in the following slides, but here. So let's say you have first sentence, apple is great. Second sentence is apple is good, and third sentence is I like mangoes, right? So apple is in the for the text one. Let's say you want to convert the first text into a vector form, right? So for that, especially for apple, the entry will for term frequency of apple will be 1, and since the text one is apple is good, so the length of the length of the text is 3. So it will be 1 divided by 3. 1 time is the frequency of the word apple occurring in the text, and divided by the length of the text. So that will be tf. And idf, since apple in total we have 3 texts, right? Apple is good, apple is great, I love mangoes. So n will be 3 since we have 3 data points. And the document frequency for apple will be the number of documents the word apple occurs in. So apple occurs in text 1 and text 2. I love apples and apples are great. So the this idf becomes log 3 by 2, and when you multiply it, you get the value for apple for text 1. Is it fine?
Yeah, I understand now.
Okay. So let's see visually how all this works, right? So let's say you have two text. This product is amazing, and second, review for a very unfortunate guy who got a empty box from some site he bought. Not going to specify what site, but it might happen that you just end up getting an empty box. So he was very angry and just gave this review. So first is removing all the noise. So when you remove the noise, you're going to remove this dot, this number. percentage sign, dot, and this dot. If you remove noise, emoji will also get removed. But let's, for simplicity's sake, let's assume it does not get removed. You wrote a very good regex that specifically remove these things only, right? So first we remove the noise, and when you remove the noise, you will be ending up with these two texts. All the noise is removed, and all the our text boils down to this. So that's the first step: removing all the noise, removing all the non-alphabets that you have. Second is transforming any abnormalities. Now this doesn't have any per se spelling error or any HTML tags or any hashtags. We only have this emoji here, right? So we'll convert this emoji into a word form. So if we demojize it, we'll be ending up with angry face. So this will be the converted form of the emoji, and this will be the form of our sentence after transforming any abnormalities. Next is lowercasing and splitting. So first we lowercase our these four texts. So
बोला
this, product, hate, these all are
कहाँ
in
है?
capital form, right? So you
अच्छा
can
अच्छा
convert this to lowercase format. So when you convert these to lowercase, now when you lowercase, all of them will be converted. So our sentence boils down to this: this product is amazing, and this is the lowercase format of that. Next is splitting. So you had a text format. Now you tokenize it. So when you tokenize or split it, you will be getting these a list of the word in the sentences. So this is what you have, and this is what you will be getting after splitting the text. Once you split it, you go over each word and you will be starting to remove the stop words. Now stop words in these two are this, is, and this. So you'll go and remove them, and this will be the final list that you'll be having after removing the stop words, right? So once you remove the stop words, you'll be stemming it. So after stemming, you will be stemming this amazing, empty. Rest are fine, but amazing and empty will be stemmed, right? And after stemming, this will be the form that they'll both be in. So amazing will be converted to AMAZ, and empty will be converted to EMTI, right? So this will be the final form of our texts. And next, join and return. So you'll be joining all the words in the list itself and return it from the function that you have for cleaning the data set. You can do without function, but I prefer to keep it all nice in one place. So join and return. So this will be the form that you have. So this is what it was, the text that we had, and this is what it became after we have converted it to it. So once you have both the text here, you have the text here, and you want to now convert it into a vector format, right? So these are the entries in the columns are the for count vectorizer, this will be the first row will define the frequency, the count vectorizer vector for this text one, and the second row will define the vector vector representation of this sentence after you convert it to count vectorizer. And same for text vectorizer. First entry is going to tell you about the vector form of this text one for after converting it with TF-IDF vectorizer, and second entry will be the text2 representation of TF-IDF vector using TF-IDF vectorizer on it. Now here I have the formula. So we'll be going over each column and start filling it. So let's fill it. Let's go over the each word that we have. So first word is product, right? And in text one, product only occurs one time. So our entry will become one here. So for count vectorizer, our entry become one because it only occurs one time here in text one. If it occurred two times, it will be two. And for TF-IDF, it becomes zero. Now this is very interesting since uh, this this is not usually the thing that you are going to be expecting on one go itself after learning about TF-IDF. So let's say you have the term frequency of 1 by 2. So length of the sentence is 2, and number of times product occurs in the sentence is 1. In text 1 is 1. So term frequency becomes 0.5, but IDF becomes 0. Now product is in both the both text 1 and text 2, right? So total number of documents that you have is 2, and the number of documents term this word product occurs is 2. So IDF becomes 0. So basically saying that this product may or may not be very helpful in segregating positive and negative sequence. Now think about it like this: if both positive and negative sentiments have the word product, is it going to convey a particular meaning to it? Is it contributing in any way? So that's something that TF-IDF defines it. Have emphasizes on that if the word, a certain word, is occurring throughout the corpus or not, right? So next is the word amaze. So amaze occurs one time in the text one, so the entry will become one for count vectorizer, and for TF-IDF vectorizer, the entry becomes zero point 0.5. That is, it occurs one time in text one divided by the length of text one, that is 2, that is 0.5, and log of 2 divided by 1. So amaze only occurs one time in text one, and we have total number of sentences that we have is 2. So 2 divided by 1, that is log 2, it becomes 0.3, and when you multiply it, you get the TF-IDF value for amaze in text 1, that is 0.15, right? So that's one thing. And now, since we don't have these entries in the text one, for both TF-IDF and count vectorizer, they'll become 0. And for TF-IDF, term frequency is 0, so that becomes 0, and they'll end up it and eventually end up becoming 0. All of these entries for both count vectorizer and TF-IDF vectorizer, right? So next thing, let's go over for this again for text 2. Now let's fill our second row. For first column, that is product. Product occurs one time in text 2, so this becomes 1. And same for as before, since product occurs in both the sentences, IDF value ends up becoming 0, but term frequency becomes 0.2, unlike before, which was 0.5, because this time product occurs one time in a sequence of length 5, in a sentence of length 5. So it becomes 0.2 into 0, that becomes 0. Next is amaze. So amaze is not in the text 2. So term frequency becomes 0 and TF-IDF value becomes 0. And for count vectorizer, since it doesn't occur, so it becomes 0 too. Next is empty. Now empty occurs one time in text 2, so it becomes 1. And in TF-IDF, it becomes 0.2 into 0.3. So occurs one time in a sentence of length 5, that is 1 by 5, which is equals to 0.2. And for IDF, it becomes 2 divided by 1. Since we have two text divided by amaze occurring in only 1.3, so it becomes 0.06. And since the structure is same for both, it will be all the entries will be 1 and 0.06. Same for hate and same for angry face, right? And that's how it all works. So let's just go and take a look at how all this works in code. And after that, we'll be learning about word2vec and how you can use RNNs to work with it. So let's start with this, and let's import our emoji library first, right? So we have already installed emoji library. Now, in order to use the stopwords, you need to download it. So you just have to run the script to download all the stopwords that you'll be having. So we'll be having our removing HTML, demojizing it, and you will be using stemmer. So we have imported all the dependencies that we need to. So here is the data set that we have. It's a sentiment analysis data set from Kaggle that I extracted, not extracted, downloaded. So that is it. And let's take a look at how many sentiment per word we have in the data set. So we have positive sentiments, about 8,500 positive sentiments, and 7,700 negative sentiments, which is really great. If it was imbalanced, that would be a problem, since we have to tackle it a bit different. But since it is fairly balanced, it's not an issue. We can just go it with normal things, right? So that's good. And here I have a function that's going to convert clean our data set, right? So first thing I've defined with stemmer here. So we have defined a stemmer instance here, put a stemmer instance as stemmer. We'll be fetching all the stopwords that we have in English language in a variable called stop. And in clean text, we'll start by it takes input as a text, and in the end it's going to return a clean form of text. So what exactly happens? So first we are going to demojize our text. So text will be first demojized. If it has any emoji, it will be converted to a word, right? Now when we have we have, let's say, some sort of HTML tag with it, so we'll be removing all the HTML tags that we have. So document from string, and we'll be just running the script, and it will convert fetch take input our text and just remove the remove those HTML tags and return a cleaned text to it. But sometimes there is some sort of parser error in it, so this is just basic exception handling that I added to take care of that error. So if you don't install it, it's fine. You may or may not need it depending on if you are getting the error, right? So may or if you, not every time you are going to get that error, so depending on if you get it, you can just add an exception handler and go on with it. Next thing is removing all the hyperlinks. So this is a regex that I added. Basically what it does is it's going to find all the words that are going to start with HTTP and remove all the remove it until it gets it gets a white space or space or comma, anything. Next, once we are we have removed our hyperlinks, we are going to remove all the non-alphabet characters. So this is the regex for that. It's going to remove everything that's not an alphabet and a space. So it will be and if let's say there is one in it, it will all be replaced with a space, right? So that's the regex for that. Next is lowercase and split. First, we lowercase our text data, and then we'll split it. Using split, we basically convert it into a list of words instead of a normal string. And this is basically a list comprehension. What it does is, let's break it down. For word in text, so it's going to traverse this list that we have, this list of words. It's going to traverse every time. And for word in text, if the word is not a stop word and the length of word is greater than 2, then stem the word and add it in the list. This is basically what it does. It traverses over that list of text, list of words. It's going to confirm if the word it's traversing is a stop word or not. If it's not a stop word, don't add it. If it's not a stop word, add it. And if it has a length of per se greater than 2, so why I have written this condition, length word greater than 2. So if there is any entry, let's say VE or EM or any sort of entry like that, I usually don't need it. And if it's not converted removed by stop words, this will eventually remove it. So that's one thing. And if these conditions are fulfilled, it's going to enter the stemmed entry of that word to the list. And after once we get that
Samir,
list,
I
yeah.
have a question actually. In this function, you are using only stemming, but you're not using lemmatization. Can you please tell me which one gives more accurate results in terms of modeling or machine learning?
Uh, so, like I said, stemming and lemmatizing are basically doing the same things. So, but with there is no hard and fast rule that says stemming is always going to be better, lemmatizing is always going to be better. So, usually, what happens is when you use lemmatizer, you also have to find the POS tags related to each and every word that you're going to be having. So, based on that, the lemmatizer is going to lemmatize it, while when you are using stemmer, it does not care about it. It's just going to stem it as it is. So many times what is going to happen is lemmatizer is going to may affect the number of features that you have, so that might affect the accuracy a bit. But nothing is for sure. Like sometimes lemmatizer performs a bit better, sometimes I've like most of the time whenever I use lemmatizer, it usually gives bad performance. Like I'm not saying it's always going to give, but every time I use it in competitions, it gives a bad result. So I usually end up using stemmer. So stemmer really improves the performance. So most of the time this is my first go to before doing anything. But there is no surety that lematizer is always going to be performing bad or anything like that, right? So that's why. I hope it's clear, right?
Yes.
Okay. So lastly, you are going to just join and return, right? So let's take this as an example. We have a really bad string here that's not clean at all. But yeah, for us it conveys a meaning, but for the model might not be. So let's run it. this was the string that we have. We remove this hyperlink. We remove this colon here. We remove the all the stop words and all the short words that it has. Removed any sort of details that we don't need, and eventually it boils down to trying product fire, right? So if you just look at the structure, like obviously this is not very meaningful, but essentially you kind of get the meaning that is it's going to provide, right? So yeah, this whole sentence boils down to this: trying product fire. So let's apply it to our data set. Like, right, we have a function, and with we'll be using pandas apply utility to just apply it over all the text that we have, right? And while we are at it, we have the labels in a string format, that is positive and negative. So we are going to be replacing positive with 1 and negative with 0. So after doing that, we'll be having these here, right? So these will be the final data that we have. And after that, let's split and test out our model itself. So let's first convert TF-IDF these sentences into TF-IDF entries. Now, one thing I really want to tell is this is very interesting. Like a TF-ID vectorizer itself is not a separate implementation, but it's actually a combination of count vectorizer followed by TF-IDF transformer. So it's just an interesting detail to know, but yeah, not very maybe any helpful in understanding per se. But it's interesting fact to know that TF-IDF vectorizer is a combination of count vectorizer followed by TF-IDF transformer. And now let's use multinomial NB and fit it. Once you have fitted it, let's see the score. Yeah. So yeah, recall is about 0.9 for positive entries, 0.83. So overall a decent result, I guess, right? So yeah, good here. So this is the code for the TF-IDF and how it is used in coding. So let's talk about, we have talked about how sentences can be converted to vector, but here is a very interesting concept: how you can use words as vector. But before that, why?
I think we lost him.
Yeah, sure. We've lost him. I hope he's aware.
Hello? Hello?
Yeah.
Can you hear me?
Yeah, we can hear you. It's not ours, the speaker's internet connection. So let's give you a few seconds. Let's wait for him. Okay, meanwhile, just give him a few seconds. I will check whether what's the problem?
Okay. Okay. Just if you can, I don't know whether that Jupyter notebook in collab
You need to have your Gmail.
is
So
available. If there's a link to it,
you
that's what I
just type.
want.
I mean, what you're
Eh?
trying to say, you don't have Google Colab, is it?
Hello. I say if there's a link, if he has the Jupyter notebook available for us, he should provide it. How would
Okay. Let me wait for the speaker.
hello? I say how are we gonna get the Jupyter notebook?
Let him share later. Or first.
Oh, okay, okay.
Yeah. So let me just open up very quickly. Collab. Screen visible?
Yeah, we can see your screen.
Yeah, we can
Okay.
see.
So from where did I left? If anyone can tell me.
We were about to
What
begin
are
with
vectors?
vector.
Okay. Yeah. So
Hi,
uh,
is it
yeah.
possible to share the notebook link at the chat box?
Yeah, sure. We'll be sharing all the resources like slides and both the notebooks to after the session is over. Right. So vectors are basically a representation of words in a 1D array, right? That's basically what vectors are. And in order to measure how similar to vectors are, we can simply use cosine similarity. And the basic goal of converting words to vector is to understand the basic context of a word. So let's say machine and machine, both basically have same context, so they'll be relatively nearer to each other, and that's what we want to achieve by converting words into vector, to get convert a word into vector such that the nearer words have more similar context to it. Now, we can use various methods to convert words to vector, but let's start with a popular one. So let's say word to vec is one of the most popular ones. So it's basically a shallow neural network that you train over a data set that you create. How you do it, we'll be taking a look at in a while. But the intuition, it's a neural network that we're going to train over the text data that we have. And the thing is, if we put a stone, let's say stone, we pass it into the word to vec model, we are going to get a vector representation of this stone word. So the length of this vector is something that you can play with, and to use this, you can use gensim library, which has the implementation of word to vec for it. And second is embedding layer. So this is the thing that you'll be using in whenever you are using RNNs to classify. Usually this is what you use. So it's another basically another layer. It is basically a lookup, like a lookup table, right? So let's say at 0th index you have the word pen, and at 0th entry of this the 0th row of this table will be having the vector embedding of this word pen. Same for pineapple. The second the first index of this table, that there will be vector representation of the word pineapple. And in its essence, it's basically just a linear layer. So if you just manually convert your word to into a one hot encoding vector and then pass it to a linear layer, that's basically what your embedding layer is doing, except now you just passed integers. So what you do, we'll take a look at a basic overview how it is done. So those embeddings that you use are going to be specific to that particular data set, not generalized ones like you can use anywhere. But yeah, you can save them and use them anywhere if you want. So you can also initialize with pretend with. Let's say you are you have a vector, a lookup table already ready with you for Twitter dataset or Instagram dataset, and if you have the similar use case, you can just load these weights into the embedding layer itself. So let's see how word2vec actually works quickly. So the intuition is basically I have a sentence, right? I have a sentence. I like your notes. So what it's going to be doing is it's going to be taking one word I and going to be outputting a vector corresponding to the word2vec. Same with like, it's going to take input like and then output its vector. Next, you are going to be taking your and then going to be output its vector. Then same for notes. So in the end, when you pass a text here, you are going to be having a 2D array where each entry is going to be defining the vector of the vector of the the word that's corresponding to that index. So in 0th index, you have this which is the vector representation of the word at 0th index here. So that's basically the intuition of word2vec. Now, very quickly understanding the how this whole works, a very basic overview. So let's say you have a sentence. Like here is the sentence that you have, which is a very famous quote from Naruto. So let's say, uh, and one thing you have to specify is window size. So let's say we take a window size as 3. So basically, what it specifies how much far you want to look, right? So since window size is 3 and you just make a window here. So first entry is f, right? And around f there is u, and on the left side there is nothing, so we just ignore that. So for f, we know that u occurs in the neighborhood, right? So we add the entry f and u in our training set that we have. And next we are going to traverse to the next word. We know that u with the word u, if and don't occurs in the neighborhood. Now, how long this neighborhood, if you want to add like your, like if you take window size 5, it's going to be adding like 2, right? So that's one thing. You occur with you, if and don't are bound to occur nearby to that word. So you add both of them to your training set. Next, you go over with don't. So in the neighborhood of don't, you and like occur. In the neighborhood of don't, you and like occurs. So that's how you make the training set, and you just traverse over the whole sentence and then just keep adding it to the training set, and that's how you get the data that you want to train over. Second step is training the model. As I said, it's a basic shallow neural network, and this are the number of words that you're going to be having in the whole corpus that you have. So all the words that you're going to be having in the whole data set that you have. So this is the size of that, which is basically the size of vocabulary that you have. So you are going to be taking the data, use it to train the model, and in the end, what you expect from this output layer is that these, as I said, these are the words basically. So this may be word apple, this may be pineapple, this may be some other word. So what we expect is the probability of let's say I pass input a word pineapple, and what I get from these are the probability of these words that they will be occurring nearby to the word that I passed as input. And but how does this work? Like if probabilities are same, let's say two words I passed as input have similar probabilities. If they have similar probabilities, these weights will be the same, and that's what I'm going to be talking about next, is getting a embedding. Now embedding are nothing, you just extract these weights. These nodes are essentially weights, right? So you just extract these weights and you are going to be having a lookup table with you. So if these weights are same, then probabilities are going to be same. And if the probabilities are same, that means the words are more similar, and that's the intuition. Same probabilities means similar words, and similar words means these weights will be will be also same for that word, right? So that's how it works. And the technique that you just learned is called skipgram. And in order to improve it, you can use negative sampling to use it. We are not going to be going into details of negative sampling, but if you are interested, you can read the blog written by GLMR. He has written a good blog on word2vec, how it works, and he has used pretty good animations and stuff to explain it all that. And if you want to go over to the intuition again, you can read Chris McCormick's blog. I'll be adding the links in that in there too, right? So these are the few things about word to vector. Now we have done converted word to vector, but so what do we do with this, right? So basically we know that sentences are kind of like sequences, right? Sentences are word followed by another word, right? I am great or I am good, right? So each word follows another, so it's basically like a sequence of words, right? And we all know that words are essentially vectors. We can represent words as vectors. So can't we say that sentences are essentially sequence of vectors, right? But so what? Like sentences are sequence of vectors. Yeah. So what can I do with this? So fortunately we have a very sequence friendly neural network in our deep learning family, that is RNNs. And we can actually use RNNs to capture the context of whole sentence a bit better than ML models, right? So let's say not good. Essentially, not good is going to be converted to separate features. But here, RNN can maybe make some context out of it. So that's something we are looking forward to, right? So a quick guide to what RNN mod, how you can use RNNs for TC, and this is very technical, basically a technical overview of the architecture that it follows. We are not going to be going to details how RNN models work and all, but just an overview if you're going to make a model out of it, how the architecture should look like. So first is the embedding layer, obviously. So you're going to be having an embedding layer. You're going to be having a text. You're going to let's say this is the first data point that you have. You are going to be having embedding layer. So you pass this into there. But problem is this is text, so you can't exactly pass it as it is. So again, what should you do? You convert these to integer tokens, and these integer tokens are nothing but indices of this word for the lookup table that the embedding layer has. So let's say at 102 will be the at 102 will be the corresponding vector entry for the word this. At index 203 will be the vector entry for product. At 8 is, and 52 amazing. So convert these words that you have into integer tokens and then pass it to embedding layer. And after that you'll be getting a 2D matrix that's going to be containing all the vector entries. So
I
that's
have a question actually.
yeah.
Is it a good practice to use text cleaning before running RNN?
That's what I was going to be talking about. RNNs basically when it comes to RNN, like what I usually do is I apply basic cleaning first, right? The very raw, like removing numbers and removing hyperlinks and all that. Like basic cleaning exists, like you would do that. But when it comes to removing stop words or stemming, you should first of all stop words usually removing stop words usually give bad results. Like for the data set that I showed you, the results were much worse when I removed the stop words, right? So don't remove the stop words, but yeah, you can try with stemming. We can play with stemming. There are actually numerous research papers that try to showcase the effect of stemming over unending. So one research paper I read was on Arabic text classification. So for some corpus it gave good results, for some it gave bad results. So that portion is experimenting, but yeah, since RNN are very sequential friendly, so context is a structuring might affect it. So keep the stop words. You can try removing it, but yeah, that's my first thing. I don't remove the stop words. I do very basic pre-processing and then I build up on that. Right. Hopefully it's clear, right?
Yeah, thank you.
Okay. Once you get these embeddings, you're going to be passing it to the RNN layer. So our first word, all know like RNN, right? We put an input and a hidden state keeps updating, and in the end, you're going to be having the final output, right? So let's say the first entry at the first time step, you give this the vector representation of this into RNN, right? After that you're going to be giving weights are updated, something happens, and then you're eventually passing at time step 2 the entry of product, right? Again weights are updated, something happens, and then you are going to be passing is vector representation of is at the time step. And again, something happens, weight updated, right? What happens is something you can look into, right? Not assuming that everyone is familiar with RNNs or how neural networks works, but yeah, you can certainly look into it and see how it actually happens. And then we are going to be the last time step that we have, that is amazing. We are going to be passing into RNN, and we are going to be getting our output vector. Now, this output vector is very special. Like as I said, output is not like you are going to be getting at end only, right? So you are going to be getting output at every time step, but you ignore them and you only want to use this last time steps output vector. So once you get this out, what exactly is this output vector? So let's say this is the context of a sentence. At the end, this output vector will be the context vector. Now you can do numerous things with this. You can use this vector to generate another sequence of words. You can use this to classify sentences. So this is a something about the last time step. You are going to be getting an output vector, which will be a context vector containing the context of a sentence. And what do you do next? You are going to be using this vector to classify this context into a sentiment. So you have a fully connected layer or normal neural network. So you're going to be having a normal neural network here. You're going to be passing context vector into it, and then you're going to be getting a text sentiment, and that's how it works. So at first you have embedding layer, then you have RNN layer, and at the end you have linear layer. So you can certainly play with architecture, how play with the architecture of fully connected layer. And if you want to get really funky, you can, instead of using embedding layer, you can try embeddings of let's say some other SOTA models or something. Yeah, so architecture is something to be played around with. And I have like, I'm not going to be going to details with the code, but I have added a notebook. I'll add a notebook. I'll add a notebook that you can take a look at to understand the working of it. Yeah, we'll be taking questions at the end. Kindly wait for a second. We are almost done with it. So sequences are done. What next? How should you go about from here, right? So I'll say first get familiar with all the RNN working of RNN on all, and word to vec, explore other methods if there are any, and just get very comfortable with what I have just told about RNNs, LSTMs, how you can use this, and architecture and all. And after that, you can try these three things. So first is Elmo. Now the problem with word to vec is if two words are same. Let's say the first sentence is "You are nuts," and second is "I love nuts." So the vector embedding for nuts and nuts is same in both the text, but context is different. So Elmo tackles that issue. Elmo changes the embedding of the word depending on the context it is used in. So it's essentially a set of bidirectional LSTM clubbed together. So yeah, so that's Elmo. And second, you can try with attention and transform models. So I'm pretty sure if have heard about NLP, you're familiar with attention and transform models, right? So you can learn about transformer, what is attention, problems that it addresses. And finally, once you're comfortable with everything, you can go on with SOTA models. You know, just understanding basic SOTA models like BERT, Silbert, Roberts, and ExcelNet, problems that BERT solved that Elmo had, and problem ExcelNet solved that BERT had for classification. And Hugging Face is usually the go-to library for transform implementation. So yeah, thanks. That's it. If you have any question, do let me know.
Actually, that part was not clear. I mean, where we are taking the word embeddings as the input and in the fully connected layers and getting the output as one hot vector. Actually, I'm not clear that we'll get a one hot vector
No, no,
because
no.
we'll get
So,
one and the other says zero. But how can we be sure that this one hot vector represents the index of the word in the vocabulary?
so like as I said, the in embedding layer, your word is first going to be converted to the one hot encoding. So as I said, you might have seen, right? Let me just share the screen again. Hmm. Right. So you tokenize them, right? 102. This word, the integer token for this word, this is 102. So you will be converting 102 to the one hot encoding, and this is all happening. Like you are just passing these integers internally. It's going to be converting 102 to one hot encoding, and then just pass it to another linear layer, and then you'll be getting the vector representation of this. So if for 102, it's going to check up in the lookup table at index 102. What is the like this? This is our basically matrix operation, but let's say there's a table and you're going to look it up. So at 102 index, there's the vector representation of this. At 100 and 203, there is going to be the vector representation of product. At index 8, there is going to be vector representation of is, and so on. Is it clear? A bit.
Yes, I think.
Hi,
Okay.
I have a question.
Yeah.
Okay, I like to ask regarding the once the text has been vectorized, and then we have made it as a tokenization and embeddings. Okay,
Hmm.
so is it compulsory for us to do the padding? No, we have a set of padding and then feed it into the ML model, or I mean, what criteria we need to look into in order to make the input sentence of the character's length to be fixed or not? Yeah.
Yeah, so usually what you do is you first take the text corpus that you have and find all the length of all the sentences that you have, right? Now this is a hyperparameter kind of hyperparameter that you can play with, right? So what I do is I just create a histogram of that and just see at what just intuitively look at how at what point I can take as a threshold for the padding point, right? So if I say I can see that after 100, there are almost negligible entries in the data set. So I take that as the point.
Uh, got it. Thank you. Oh, I have one more question.
So,
Just now we saw that it is not a proper English text of the sentence, right? And we
right,
have some kind of library we call spelling error. So for the case of some text might have the slang, right? So
right.
when we mention slang, like what kind of method should we use in order to handle that use cases? Yeah.
So I particularly like right now there is something called style formers, right? That is able to convert slangs into actual meaning that they convey. So like you say "you are" is going to be converted to "your," something like that. But as of now, what I do is there's a link on GitHub that is going to be having mappings of each slang to the other. It's basically CSV file. So I import that and create a dictionary for it, and then just go over if it's a slang, then I just convert it into the dictionary mapping that I made.
Cool. Got it. Thank you so much.
No problem. Any other questions in the chat?
Hi, thank you very much for your presentation. I
No
just have
problem.
a general question on the data set. Earlier you showed a data set of Twitter, right? So, not Twitter, sorry. Product reviews, and there's positive and negative sentiments,
Yeah.
right? So, if you were just going by the general idea that you are going to collect information about product reviews without a specific goal, how would you go about like labeling those data set? Uh,
First you have to obviously you have to scrape the data set, right?
Yeah,
And
so
after
after scraping,
so let's say you have Amazon data set, right? So first thing
right?
I usually do is I just check out if there are any existing models in Hugging Face or somewhere that are going to be able to help me label that. Right? That's the first thing I do. And once if let's say I find some model that is going to be able to do that or do all that, I just do it, and then it's just a matter of verifying all the labelings. But many times it may not happen that I have a model that is able to do that. So usually like recently came across this issue. I had the data set but I didn't have the label. So what I did was I tried another data sets that I have to train my model. that might be able to capture similar meaning, maybe if it's, especially if it's a positive sentiment analysis. I usually train it over the different data set and then try to label that, and if it's performing well, I do that. Else, I just manually have to label a few entries and then automate the process.
Okay, right. So you're saying find existing model to classify for you whether it's positive or negative or something
Yeah.
simple like that, right?
Yeah,
But
so
what
like,
if the use case is slightly more complicated, if I may share. If let's say you are finding out about mental health and you are not sure what are the categories that are available, like whether
right.
it's not a simple positive negative thing. How might you go about doing it?
So yeah, like again, I have to first be sure about the data set that I have is, uh, you know, the data set that I have is, able to match it correctly. So recently, I also had a problem that I had to deal with, a data set regarding mental health. Right. So what I did was I went over to Reddit for the to the subreddit of the corresponding entry, and then I was pretty sure that the entries in this subreddit are having the correct context that I wanted. So I usually use that, and then I trained my model, and then the data set that was provided to me, I just trained it over it. So my
Right. So
was yeah.
so you basically label all the posts from that subreddit as a
Yeah,
mental health data set, is it?
yeah,
And
yeah,
then
because that subreddit was dedicated to that.
right, do you have non-mental health data set to train the model as well? Just to see the
Regarding
difference.
when it comes to non-mental health, so let's say there is movie reviews, let's say, right? So for movie reviews, we have already pre-trained models in Hugging Face for IMDb, Rotten Tomatoes, and all that. But if we don't have that, usually you can try labeling some data points, and then using those points to classify other points, and then just verifying. Like, verification is something that you have to do, else you are just unsure about if it might be or might not be.
So sometimes manually labeling may be required as well, not
Yeah,
just
yeah, yeah. Sometimes it is required, but usually I try to find alternatives if possible.
right. What are some of the possible ideas to like manually label? Like what do you label it as? Like I mean it depends on context, but let's say
Yeah.
for product reviews, what might you label them as besides just positive and negative? And how do you
You
come up with those ideas to label as,
so
what category?
if you are trying to label it as positive or negative, let's say reviews. So for reviews, you can try and get the rating also, right? If you have a review, you also have a rating associated to it, right? If you're especially using a big retailer sites like Amazon, Flipkart, right? So
Right.
using those review, you can classify it as positive or negative. So this is something I do, that if it's greater than 4, I make it positive. If it's less than 2, even on Kaggle you can find various notebooks for this implementation, right? There is a pretty good data set, that is Amazon music reviews data set. So that's the approach they took. Like, above 4, take it as positive; 3, take it as neutral; and 1 and 2, take it as negative, something like that.
Right. Then okay, maybe one last question. Then how would you handle the mental health one in your case? Like how do you categorize it? Like what do you label as, like the subreddit's name or
Yeah, so no, so mention it that I can't go into much detail right now, the paper is not published yet, but let's say I have mental health issue A, so I label it as A, not A. So mine was a very extreme data set, right? So on one extreme, I just labeled it A, and for the second portion, I extracted a post from happy subreddit, right? So people usually celebrate their victories and whatever they are feeling happy about. So that's something you can also go. There is something called as talk life, where people talk about their issues, which specifically mentions the mental health issue these people are facing, right? Anxiety, bipolar, or depression, like that. So you can scrape from there too.
okay, I think I get the idea. Thank you very much.
No problem. Yeah, Raju.
Actually, I have a question. For example, like for computer vision, we have libraries like GradCam to visualize how which part of the image is contributing to the classification task. And is there any such model for natural language processing to visualize which words are actually contributing to the classification?
Yeah. So you can use word clouds to do this. Like there is a library called word cloud. You can use that to visualize it.
I mean, actually, isn't workload based on the just based on the data set? I don't think it's based on the machine learning model.
So you want to maybe okay. So you want to maybe contribute check which features contribute to which word contribute to that, right?
Yes.
I'm not sure about this. I'm really sorry. I'm not sure about this. I never tried this. Yep. So Surya is asking about any good resources on Transformer for understanding it from scratch. So for Transformers, I guess JLMR has a good blog series about Transformers, and there is actually a blog on analytics Vidya you can use, right? And there is also a great course that is released by Hugging Face that you can go through to learn about Transformers, right? Could you recommend when to use which vectorizer, count versus TF-IDF? I guess in Max case, you are going to be using TF-IDF. Like using count, you're not going to be able to capture the relevance of the word throughout the whole corpus. So TF-IDF is usually the go-to. But yeah, sometimes when there are many competitions in which people actually use count vectorizer. So it depends on the task. But whenever they use it, they just added up the whole feature set into one feature. So yeah, it's like for if you are actually making a project, TF-IDF should be your go-to. Can you please?
Can you share some resources where I can learn about how pre-training is done and how we can use pre-trained models on how we can fine-tune pre-trained models?
So yeah, I'll be sharing a course from Hugging Face themselves. So Hugging Face course. Yeah. So this is chapter 1. I've shared the link here. And collab presentation. I'll be adding link here. This is the collab presentation. And collab links. Share. This is the collab link for LSTM. And this is the collab link for Knife Base. Anything else? Any doubt? Anything?
Can I asking something?
Yeah, sure.
That was wonderful presentation. Thank you for that. So, can you share some resource or technique tips for such a good presentation? As we often have to present something.
Yes. What I do is for templates, I have this site called PPTmon. So you can add templates there, and for the visual part, I add draw everything on Canva.
Can you share the link or resource?
Yeah,
Please?
sure. So, yeah, since we are out of time,
Thank
this
you.
will be our last out. And so, if you have any doubt, you can go to my LinkedIn and DM me. I'll add my LinkedIn here.
Hi,
PPT
Kiran.
mode.
Is
So,
notebook link is available?
excuse me?
Is the notebook link available?
Yeah, I have added it in the chat.
Um,
Okay, sorry. I've shared it right. Yeah, just a second. Here's the Canva. I'm really sorry. I just sent it to someone else. Yeah. So can you see the collab notebooks now?
yes, yeah. Thank you.
Yeah. Okay. So I've posted Canva link and PPTmon link for the one who's asking. Thank you. That's it. Yeah. So that's it from my side. And that's our app. Thank you for attending. It was really great to be able to give back to the community I've been a part of, and that helped me grow throughout this. So thank you, Sharon. Thank you, Madhu, for that.